So, we were discussing deoxidation of steel, and we are on the verge of completing our discussion, and I would like to reiterate before I initiate discussion on Ladle and Ladle Metallurgy today, that deoxidation is a very extremely important step, and it has profound implication on the economics of steel making as well as the quality of the product. So, therefore, it must be carried out, and in that context perhaps nothing is more important than to ensure that the deoxidation product does not remain entrapped in steel to a large extent. So, the more the more the steel is devoid of deoxidation product, the better is the quality, better is the cleanliness, and that is what is desirable. And there a lot of engineering is involved, and I will try to address some of these when I talk on Ladle metallurgy and particularly the calcium injection. So, you perhaps, because deoxidation products form due to nucleation and growth, and there would be a huge size range of such products, and it is well known that to get something eliminated in ladles which have a size range of less than 30-40 microns is going to be extremely difficult, because you require enormously long time to get them floated, and that is perhaps not desirable, keeping in mind the continuous heat loss from the vessel as well as loss of production time. So, one has to make a compromise and one has to develop a strategy, and some of these we are going to utilize or study later on. Now, I missed to give you one important plot which is generated on the basis of the equilibrium of the deoxidation reaction, and there the plot is basically given in terms of wet percentage X versus wet percentage oxygen, okay. And that is what is given in logarithmic scale. This axis is in logarithmic, this is logarithmic scale and this is logarithmic scale, and then you can imagine that you will get always a straight line, because for example, if you write the aluminum deoxidation reaction, then aluminum raised to the power 2 will become 2 log aluminum, and similarly aluminum oxygen raised to the power 3 will become 3 log oxygen. So, you will get a straight line, and these are all equilibrium values. So, and this value, if I remember, this is about 1, this is about 1, this axis is about 10 to the power minus 3, and this is about 10 to the power minus. And the lines go something like this. This is zirconium, and I am only showing those elements which are conventionally used or customarily used in steel industries for deoxidation. So, this is there, and then we have titanium, boron, silicon, and perhaps manganese is here. So, list most weak deoxidant. On the other hand, strong deoxidants are zirconium, and this could be titanium, this could be boron, and this could be silicon. Okay? And there you can say that this is possibly, you can, if you divide it into 10 to the power minus 2, 10 to the power minus 1, and 10 to the power 0, and that is equal to 1. And here also you can have that is the kind of axis. So, and this are based on thermodynamic calculations, equilibrium calculations, where you take from literature the value of the equilibrium constant, and these are also valid for, I think, steel making temperature, and that is at 1600 degree centigrade. So, I would also like to demonstrate, before I end lecture on deoxidation, a sample calculation, and to illustrate this aspect of deoxidation calculation, I just want to emphasize that yesterday I have mentioned in the last lecture that deoxidizer, a part of the deoxidizer goes inside the metal, stays in the dissolved form, and a part of the deoxidizer reacts with oxygen, and that is an oxide product, that is the deoxidation product, and that floats up. So, the deoxidizer gets partitioned between the bath and the deoxidation product, and I would like to demonstrate that the largest chunk of deoxidizer is actually sitting in the metal itself, and that chunk is largest for manganese and smallest for aluminum for a given oxygen content, and that we have to remember. Let us take a case and let us say that we have a ladle, a small ladle. How much? We have 60 ton capacity ladle, so which is about 60,000 kg. Let us say oxygen final, oxygen initial is about 700 ppm. That is typically what we have seen, about from 400 to 600, that remains that is the equilibrium range of, it depends on carbon content of course, and the desirable oxygen final is about 100 ppm. And yesterday I have also indicated that possibly this kind of a reduction, final oxygen 100 ppm will be good if you use deoxidizer like silicon or silicomanganese. On the other hand, if you want to go to 10 ppm or 20 ppm, then perhaps you will go for aluminum, we must remember. And when we have too little oxygen content in the bath, final equilibrium bath, and then we say that the steel is basically kill steel. That means there is no scope for any further reaction with oxygen, and this essentially represents that if you the amount of oxygen in kg which is eliminated. So, if you do, you have about 60 ton, so 42 kg, and you have 6, so 42 minus 6, and that gives you about 36 kg. This much of oxygen you are going to remove, and this oxygen you must remember, where will this oxygen go eventually? This is going to go entirely into the deoxidation product, and this much of oxygen is going to be there remaining in the metal, okay? And this will be in equilibrium with the dissolved deoxidizer content. Let us say that we are trying to deoxidize with silicomanganese the bath, and that the deoxidation product chemistry is known to us, that is 45% silica and 55% MnO, which essentially means that the molecular formula of the deoxidation product is 1 mole is to 1 mole, that is the deoxidation product. So, this is the data given, and I want to now find out that how much of deoxidizer needs to be added, how much of deoxidizer is in the metal, and how much of deoxidizer is sitting in the deoxidation product. So, I want to demonstrate there are two parts of the calculation. I will illustrate the concept of material balance, I will also illustrate the concept of thermodynamic equilibrium. Now, if you take the deoxidation reaction Si plus 2 oxygen giving you SiO2 solid, the deoxidation product, and you have K equilibrium is equal to activity of SiO2, and this is, we can, if you say that the activity is proportional because they are dilute solutions, as an approximate, is reasonably good approximation is that weight percent SiO Si and weight percent oxygen square in 1 weight percent standard state. Okay? So, we can, activities can be represented in terms of their respective weight percentage. So, K equilibrium value, as I have indicated from thermodynamic handbook or chemical, or metallurgical engineering handbook, you should be able to find out. And let us say that we know the value at 1600 degree centigrade, and let this value be 4.2 into 10 to the power 5. This is a large equilibrium constant value, which essentially means that the silica is a fairly stable phase in this particular case. Okay? And then we have activity of silica, this is not equal to 1. Okay? And I would say that this I will write down as this, which essentially means it is in combination with some other phases, and it is there as MnO SiO2. So, its activity is going to be less than 1. How do we know the activity? Because we know that the deoxidation product is 45% SiO2, 55% MnO. So, we should have now what is known as an activity composition phase diagram. Activity composition diagram is needed. So, for complex deoxidation problems, activity composition diagram. Simple deoxidation problem, we will not require that, because simple deoxidation means alumina will form and alumina in pure phase, so its activity is equal to 1. So, there is no need of activity composition diagram for simple deoxidation, but that is a complex deoxidation. If you have 2 or more elements participating in the deoxidation reaction and the deoxidation products are a combination of multiple oxides, in that case what you require is an activity composition phase diagram. These diagrams, composition diagrams, are available, okay, for various systems, and it goes something like this. For example, for MnO-SiO2 system, it goes something like this. So, what is there on this axis? It is percentage of SiO2, and on this it is either activity of MnO or you can read activity of SiO2, okay, and this possibly is somewhere around, say, I would say 50%, and this is the composition that we are talking about, okay, and this is say 45. What does this line indicates? This line, the red line now I have drawn, is corresponding to activity of SiO2. So, from this line you are going to carve, you are going to read the activity value, okay, and this is the 45% composition, which is the deoxidation product. So, it means when the deoxidation product has a composition of 45% SiO2 in a mixture of SiO2, MnO-SiO2, then the activity can be read straightforward from this, and this value comes out to be 0.6. Similarly, this line therefore by default is the activity of MnO line, and here it intersects, you know. So, 45% is SiO2, then 55% is MnO. So, corresponding to 55%, one can say that this is the activity, and this activity comes out to be 0.14. So, now equilibrium constant value is known to us. Final oxygen, this is the oxygen at the end. So, this is OF, I would say, and this is the silicon which is in equilibrium, and that is the calculation that we are performing. So, if we substitute 0.6 here, activity of SiO2, if we substitute 0.01 as a final oxygen, if we substitute K equilibrium is equal to 4.2, there is only one unknown, wet % silicon, and the wet % silicon will come out to be something like 0.14 wet percentage. There may be a little bit of difference in the calculation, okay. The values, exact values I do not remember. So, I am just putting some approximate values. So, this is what it is. Similarly, we can do Mn plus oxygen, and the same calculation if you do, then you will find out that with activity of MnO is equal to 0.14, this is, I think, this value is about 0.2, 0.2, this is the value, okay. So, activity MnO is equal to 0.2, and activity of SiO2, this essentially indicates is 0.6. That is what from this point and from this point we can infer for the slag composition, okay. And so, we can substitute activity of MnO is equal to 0.2, oxygen final is known, and if the equilibrium constant is known, and the K equilibrium here I think is 2.4 into 10 to the power 2 of the order of 10 to the power 2, and in that case one can show that wet percentage of Mn is going to be 0.58. So, we can now do a calculation 14.14 wet percentage corresponding to this much of steel, how much is going to be the silicon present, and for this much amount of manganese, how much is going to be the manganese content, and I think this comes out to be close to about 83 or 84. So, this corresponds to approximately 80 kg, and this corresponds to approximately 360 kg. That is the value that we have. So, manganese, total manganese in steel, which I have written in with yellow chalk, okay, manganese is about 360 kg and 80 kg. So, 360 kg of manganese has gone. So, that is the equilibrium part of the calculation. Now, we can see that some manganese has also gone into the deoxidation product, and that deoxidation product is MnO SiO2 to to start with I do not know that what is the weight of the deoxidation product forms. So, let me say let the product be W kg. So, I can now perform an oxygen material balance, and that material balance says that oxygen tied up with Mn plus oxygen tied up with silicon, okay? And that must be is equal to the total amount of oxygen which we are eliminating from the system. So, the right hand side can be written as 36, and we can see that the molecular weight of this is 130 kg. So, in 130 kg, as you can see here, or we can say that we have a MnO here. MnO is how much? 55 plus 16 is 71. SiO2 is how much? Si is 28 and this is 32. So, this is 60. So, we can say that 55, you know, so we have 45% is 4.45 of this is the total deoxidation. This is the W kg is the total deoxidation product mass. So, oxygen with MnO. So, in 71 kg we have 16 kg, and how much of MnO is there? So, we have total deoxidation product. So, we have this is multiplied by the deoxidation product contains, the chemistry is given 45 and 55. So, 0.55. So, this much is the weight of MnO. So, this much of oxygen is tied up in, and then we have here in 60 we have total oxygen is 32 and then multiplied by 0.45 W, and that must be equal to 36. So, this essentially indicates that in 71 kg we have 16 kg of oxygen. So, 0.55 into W kg, how much of, because W is the weight of the total deoxidation product and 0.55 W is the total MnO which is formed. So, if you solve this, then we can find out that this is equal to approximately 100 kg of deoxidation product forms. Now, I think from in 100 kg we will be able to straightforward find out that in 71 kg if 51 kg is Mn, okay. So, we have now, so Mn, how much of Mn is there of which? So, Mn is going to be mass of Mn. So, we would say in 100 kg we have 55 kg. So, 130 kg which is the total molecular weight, and then we say that 55 kg of Mn is there. So, therefore, in 100 kg of deoxidation bath how much is going to be there, and M silicon we can calculate accordingly that in 130 kg silicon is 28 kg. So, therefore, in 100 kg of deoxidation product how much is this going to be, and this will come out to be something like I think 45 approximately, okay, and this will come out to be something like 28. So, this is going to come out to be 28 or something like that. So, this is roughly about 73. So, what is the balance in that 100 kg? The balance is obviously oxygen, because I have done extracted the weight of manganese, extracted the weight of silicon from where, that I have 100 kg of deoxidation mass, and in this 100 kg I have 45 kg Mn, I have 28 kg Si, and therefore, the balance must be. So, therefore, if I sum up now 45 kg with how much I have find out. So, total Mn is 45, which is sitting in the deoxidation product, and 360 which is there as dissolved manganese. So, it comes out to be something like 405, and total Si that is going to come out to be somewhere like 80 kg, and then here we have 28 kg, and that gives us 108 kg. So, which is something like approximately 510 kg. That is the total Mn. So, therefore, I can find out that we are talking about somewhere that we have to have roughly about manganese and manganese is to silicon in the deoxidizer as I would say this is roughly like 510 and 40. So, this is about in 80-20 proportion. That is the composition. So, entire how much of deoxidizer to be added, what should be the grade of the deoxidizer in terms of silicon content, etc., how much of deoxidation product can be formed, all these things can be calculated. And one important thing is needed here, that to proceed to have the value of the activities in the equilibrium relationship, and these values for complex deoxidation are only known provided you have the correct activity composition diagram at the prevalent temperature. If you have that, then it becomes a piece of cake, it is a routine calculation. Of course, one can do more accurate calculation by taking into account the activity coefficient, etc. Okay, if you are too fussy about it, but a first hand calculation, first hand estimate, because you are going to anyway add 5 or 10% more, thinking that the slag will contain some carryover, the Ladle slag will contain some carryover slag, and as a result of which there may be some loss of deoxidizers, and that therefore, to take that into account, you may be anyway adding 5 or 10% extra deoxidizer into the bath itself. But certainly you can have more accurate calculation by taking into account the considering Henrian activities of silicon and wet percentage or oxygen into the equation. And also you can incorporate, this is a diagram which I have taken at 1600 degree centigrade. You may require a more precise diagram or an interpolated diagram, because these values are mostly given in terms of 1550, 1600 and 1650 degree centigrade, because these are the temperatures. If you have an intermediate temperature, then you will simply interpolate and find out that what are the activities of the species concerned corresponding to their respective weight percentages. So, I think that is enough for this course as far as deoxidation is concerned, and we will come back to the flotation of the deoxidation product later on when we talk about tundish metallurgy and so on. So, we will move on to now the new topic. Today we are almost 3/4 of the course is done. So, now on lecture 30th we have Ladle and tundish metallurgy for the next and tundish metallurgy. For the next 4 lectures or so, we are going to spend time on ladle metallurgy and tundish metallurgy. Now, the term ladle is familiar to you. Ladles, we have seen that the blast furnace hot metal is often tapped into a ladle. Okay, it is also tapped into a torpedo car. Also, we have seen that steel making furnaces, be it EAF or be it BOF, the furnace is always tapped in ladles, and the ladles have the same capacity as that of the furnace. So, we have a wide range of ladles, and I have also shown you that the ladles are basically marginally tapered vessel. Ladles have in the industry typically L by D ratio varies between 8:5. This is the typical ratio. We also know the L by D ratio of other furnaces, BOF, EAF, etc. I have told you that, and these are obviously they are going to be lined with refractories. Every ladle is fitted with a porous plug. A refractory artifact through which gas is going to be blown, and that gas is an inert gas, because now when you have tapped molten metal into the ladle, we must understand that we have carbon absolutely as per the desired level customer specified, silicon no problem, manganese, phosphorus no problem, sulfur, if you have not done pretreatment, maybe the sulfur is little bit higher, and the sulfur could be unacceptable, varying between this much wet percentage. Deoxidation we have carried out, and if you have taken deoxidation, you have if you have carried out deoxidation, in that case we can understand that we have some dissolved element, dissolved silicon and aluminum, but nonetheless we have taken enough precaution to make sure that the deoxidation is being carried out in such a way that the residual content of silicon and aluminum are not above the threshold desired by the customer. So, dissolved oxygen is therefore also correct, or if the deoxidation has been done approximately, so it may be very close, it is to the actual one, but may not be absolutely the precise desired level of residual oxygen. So, there may be some correction, some additional trim adjustment in composition, that is what we say. So, subsequent addition of change of compositions are going to be very minute actually, okay? And the scope of changing composition comes with respect to silicon sulfur and with respect to oxygen. So, this could be because deoxidation often is not carried out to completion in the during the tapping itself. It is during the post tapping and LRF ladle in the ladle furnace. This is called ladle, or also called ladle furnace. It is also called ladle refining furnace, because some further refining is going to be taking place. Okay? So, some adjustment beyond tapping will be carried out as far as oxygen is concerned. I have also told you that or we have noted that during the tapping of molten steel there is significant amount of ambient air melt introduction. So, as a result of which what happens that dissolved nitrogen, and if it is electric arc furnace, then there is a chances of contamination of molten metal by hydrogen, because I have already mentioned that electrodes etc. are water cooled, and as a result of which the moisture content in the environment of an EAF is significantly larger than that in BOF. So, nitrogen and hydrogen could also be problem. Also, we have noted that we may have carried out steel making at 1600 degrees centigrade, but the temperature has gone down to a significant level during the tapping operation itself, because of the simple fact that at high temperature 1873 Kelvin you have enormous amount of radiation losses from the surface. So, if you have carried out tapping operation for 10 to 15 minutes, there could be 60 to 70 degree drop in temperature. Now, to eliminate sulfur, to eliminate oxygen, adjust oxygen, to eliminate nitrogen and hydrogen, and also we have to give some opportunity, and as I have indicated that we have topic like calcium injection etc. to enhance inclusion flotation. So, we have to give some time. So, there are a lot of processes which are still left, because steel at this particular step, although fulfills composition grossly, it is not what we would like to deliver to the customer, or maybe it is not at the level desired by the customer. So, it requires further refining. All these things, adjustment of temperature, adjustment of composition and adjustment of cleanliness, this will require some time. How much? This could be as much as the duration of the primary steel making process, or longer than that, 70 to 80 minutes more of processing time will be necessary. And we must understand that for every steel all these treatments may not be necessary. Okay? There may be some cases where if you can carry out BOF operation correctly, deoxidation also completely, and not too much bothered about the cleanliness of steel beyond a certain level, then the steel produced, the crude steel itself can be converted to solidified product and sold to the market, but certainly not for critical applications. Okay? If you are building a multi-storied building, that is perhaps skyscrapers, not acceptable, but if you are building a single story house, or making what you call a gate of a metallic gate, steel gate for your garden, perhaps the steel which is there sitting in the ladle is good enough to work for that. So, subsequent treatment of say 70 to 80 minutes will lead to significant value addition, and there is going to be tremendous improvement in steel quality, and as a result of which the price of steel which comes out of primary steel making vessel and the price of steel after the subsequent 70 and 80 minutes of processing in the ladle and tun dish, there could be huge difference. And I would say that this at composition adjustment, temperature adjustment and cleanliness adjustment, which will now be carried out, which are carried out beyond the primary steel making process, are correctively referred to as ladle metallurgy steel making. In many textbooks you will see these operations which we are talking, composition, temperature adjustment, cleanliness adjustment and composition adjustment in ladles are referred to as secondary metallurgy, secondary steel making. But the word secondary I think is derogatory, because noting that the value addition is significant, therefore my take is that I will not like to use the word secondary steel making, rather than I will say ladle metallurgy steel making, noting the importance of ladle metallurgy to improvement in the quality of overall quality of steel and cleanliness of product. So, lot of operations now we will see will be carried, and once that is as I have indicated. So, heating will be involved, composition adjustment, heating to compensate the temperature drop, composition adjustment to control nitrogen, hydrogen, dissolved oxygen, etc., and cleanliness improvement to ensure that the deoxidation product, etc., do not remain entrapped in steel. These are my objectives of ladle metallurgy steel making process. Before we go and discuss these three things together, let us talk about the features of ladle. So, let us come back. So, the ladles are equipped with a porous plug, and through the porous plug argon is going to be blown, because we know that next 70-80 minutes the material is going to be sitting in the ladle and the processing will go on for improvement of temperature, for improvement of quality and so on and so forth. So, and the rate of heat and mass transfers are strongly dependent on stirring in the system, and we cannot use now any reactive gas. So, argon is an inert gas, and that the objective of the argon is that the argon will rise from here, and as the gas bubbles are going to rise, it is a very small gas flow rate that one uses. And what would be the flow rate of argon? Argon flow rate will vary from 0.1 nm cube, normal meter cube, sorry, this should be nm cube per ton per hour, to about 10 times more, 1 nm cube, depending on the objective of ladle metallurgy. We will look at these flow rates. This is Q argon, volumetric flow rate of argon. We will consider these flow rates a little later in great detail, that why so much of 10 times variations, and I would just, it is sufficient for you to note that if you just want to stir gently the system, so that if you do not stir, what is going to happen? There is going to be thermal inhomogeneities and material inhomogeneities. You can imagine heat is going to be continuously lost. What is the temperature here? The temperature here could be something around 300 degrees centigrade. That is the wall temperature, so which essentially tells us that heat is being lost, because inside temperature is 1600 degrees centigrade. Okay? So, we have molten metal here, and then we have a slag layer which is sitting, and this slag layer, as I have indicated, is not, it is a synthetic slag, and therefore, that is the kind of scenario that is. There is a reason for putting the plug here, okay, that I will discuss, that will be obvious to you, and these are the argon bubbles which are rising through the. So, we have no slag here. This part is called the slag eye. Okay. The slag, as I have indicated, has several functions. The slag will protect the radiation loss. The slag will protect the steel from coming in contact with atmospheric air, and also the slag will help to absorb these non-metallic inclusions which are floating up to the free surface itself. So, slag has lot of functions, and this slag, as I have indicated, will not contain any iron oxide. Carryover slag has to be minimal in order to maximize the performance of ladle metallurgy steel making processes. Also, we have a well block here, and that well block is basically to drain molten metal out. So, ladles will never be tilted like the furnace. Okay? all ladles are equipped with a bottom pouring facility. So, this is the well block. There is a little nozzle here, and we will study that there are metering nozzle facilities here. Mostly today we have slide gates which are fitted up, slide gate valves actually. So, those valves are fitted at the bottom which can control the rate of liquid flow out of the ladle. But that is when we talk of draining of molten metal from for 70-80 minutes, we know that metal is not going to be drained. So, let us not talk about it, we will come back to it later on. So, these are the constructional features, and a modern day ladle will also be equipped with a ladle cover. Okay. This is, you can say, reasonably sealed, but not perfectly sealed. So, this cuts off the atmospheric. So, as a result of which what happens? Heat loss, reoxidation. Reoxidation means, because now what is, you have 10 ppm oxygen sitting here and outside is PO2 is equal to 0.21. So, there is a oxygen is wading outside at the first opportunity itself, it will try to get into the metal which is which has great affinity for oxygen. So, because the steel is killed, because it contains only 10 ppm oxygen, there is a large difference in oxygen gradient. So, from atmosphere there is a great tendency for oxygen to pass or to dissolve into the molten metal, and that we need to prevent at any case if we want to ensure that reoxidation does not take place. Reoxidation, as we will see, will impair the quality of steel, and this slag, the synthetic slag here cover as well as a top ladle cover, physical cover, will allow us to maintain or constrain the heat loss, reduce heat loss as well as reduce the extent of atmospheric reoxidation. The ladles are lined with refractories, it is to be expected, okay? And these refractories are basically basic refractories, tar bonded magnesite, mac coke brick, that is what typically is the name in the industry. High alumina bricks also people uses. These ladles, the bricks require relining after 60-70, it varies from plant. There are plants also which can recycle ladles for 120 heats or so on. Recycling means the ladle is preheated in the beginning, because we cannot pour molten metal into a cold ladle. Once the new refractory etc. is laid, so the ladle is put in a plant in a horizontal position. Okay, the ladle lies something like this. Then we have a cover like this, and there is a hole here, okay, and you have an oxy-fuel burner through which the ladle is going to be really heated up. Okay. So, for several hours, so this is an oxy-fuel burner, and this is called the preheating stage of the ladle, and we will ensure that after prolonged heating, the ladle surface temperature will, inside temperature could be about 1200 degree centigrade or so. So, the hot ladle will be taken to the furnace, molten metal will be poured, then after the 70-80 minutes of processing time, the ladle will be taken to the caster, where casting will take place, ladle will get empty, the ladle will come back under the furnace once again. That is the cycling of the ladle. So, the ladle cycles between what? Between furnace and the casting pit or the casting bay, okay? And this frequency is about 70 times, 80 times, and up to about 120 times also ladles can sometimes circulate, and then the ladle refractories do require relining. Porous plug, it is a replaceable artifact. So, it lasts about, depending on the quality of the porous plug, 7 to 10 hits or so. Well blocks, these are closed with some material, refractory material, which tends to get sintered, and then as the slide gate they are not expected to get sintered, because if they get sintered, then they are going to be the removal is going to be very difficult for them. So, the characteristics of the well block powder which closes the hole is very important, okay, such that when the slide gate is moved, automatically the powder falls down and molten metal rushes out through it. But if the powder gets sintered with the wall, in that case what happens is the powder does not open. So, this is called a phenomena of free opening. Ladles will free open, okay? That means the moment you will pull the slide gate, the powder will come down, free flow of powder, and molten metal will also come out, okay? So, but if the powder gets welded, then the slide gate you will move, but the metal will not flow out, because the powder has got sintered with the refractory wall itself. So, it is very important, because if you do not get free opening, then you have to artificially do something, okay, and then you do oxygen lancing and all kinds of things, which again jeopardizes steel quality. So, the quality of the powder with which the well blocks are sealed is very, very important, and this is important because we 100% free opening is rarely achieved in practice. Free opening, one or two hits in 100, you will find that something has gone wrong with too much of a temperature, or erroneous composition, etc., have resulted in the sintering of the powder, which is not giving free opening at all. So, it is very important for us. Okay, we will talk about this later on. So, porous plug is going to be replaced about 7 to 10 hits, every 7 to 10 hits, and we have the ladle recycling period about 70, somewhere between 70 and 100 hits, and so on and so forth. So, here I would say that once the ladle is preheated, newly laid refractory, and the surface temperature is about 1200 degrees centigrade, then only it is taken for to be used as an LRF or ladle furnace itself. Now, the gas which you inject here, this gas undergoes, the gas rises up, okay, because the gas is lighter, because of its potential energy, and when the gas, then the gas as it goes up, it entrains surrounding liquid along with it, and as a result of which you generate a toroidal current within the system. So, it is basically a buoyancy driven system. Okay? The buoyancy force applied by the bubbles on the liquid actually manifests in the stirring of the bulk liquid, and the gas you may be using at normal meter cube, but the steel does not see the gas at normal meter cube. If you do a pressure temperature correction, then you will find out that normal means what? Normal means 298 Kelvin, okay, and 1 atmosphere pressure. Okay, this is not standard, this is normal, you must remember. There is a difference between normal and standard. So, but the temperature here is 1600 degree. So, 1600 divided by 300, which is roughly about factor of 5 or a little bit more than 5. So, 5 times expansion because of the temperature, and there is some reduction because the pressure here is going to be the atmospheric pressure plus the ferrostatic head. So, still you will find that the gas volume could be 3 or 4 times larger than the gas that you have injected into the system because of the expansion. So, the metal sees much more amount of gas than you have injected, okay, because of the elevated temperature, and that causes good amount of stirring, expediting the rate of heat and mass transfer processes in ladles. The ladles, for example, if you consider the gas flow rate, then you will find out that a bigger ladle is more advantageous and higher L by D is desirable. The efficiency of stirring for a given amount of gas. Okay? So, if you use normal meter cube, same gas, specific gas consumption rate in 2 different vessels, you will find out bigger the ladle, more efficient is the stirring, and higher is the L by D ratio, more is the stirring. And L is liquid depth is higher, essentially implies that because it is a potential energy driven system, okay, the injection point has a great role to play, which determines the depth over which the bubbles rises, and greater is this depth, more is the circulation. That does not of course means that you will have very large L by D 5 or L by D 10, that defeats the purpose, because in that case the flow pattern changes quite a bit. So, the flow pattern really looks like this. And the plant is located off the center, it is not at the central position, and this is, I would say, the mid bath radius position. So, if you look at the base of the ladle, the base of the ladle will look something like this. So, you will have something like here you will have the well block and here you are going to have the porous plug. In some plants or in some big ladles, one plug is not good enough because you use a very small flow rate. So, you require two plugs, and in that case the plugs could be located exactly opposite, and the well block may then be located somewhere here. And this position of the plug is called, which is also apparent from the figure, is the mid bath radius position. If you have two plugs, then you have diametrically opposite plugs. It does not mean that this is, there is a unique, you can have a plug here also, for example. Some plants uses a dual plug where you have this and this plug, okay? Not this particular plug. So, there are several combinations, and what I have shown here are two diametrically opposite plugs located at the mid bath radius position. So, if you have a single plug, then you would say that single plug is located also at the mid bath radius position, and this is the well block, so W, and this is the plug. The plug is never located at the center, and that will be very clear to you when you talk about this. We have, for example, the intensity of flow is very important, which will determine, people can do lot of, because you see the intensity of flow determines at what rate alloys are going to melt, alloys are going to dissolve, because these are all convection controlled processes. So, therefore, you can say that an idea of the flow intensity is important, and there are two velocity scales people normally use. What is an average speed of liquid recirculation? This is the average speed of liquid recirculation, and this is the average plume rise velocity. That means, this is the gas steel plume, how fast it is rising. Two scales of velocities are used to quantify the state of, and this is something like people write it, 1 L to the power minus 1 by 4 and R to the power minus 1 by 3. So, which essentially tells us that as you increase the gas, these are all SI units. So, this is meters per second. This is not a dimensional constant. This is dimensional constant, not dimensionless. The gas flow rate here is important to note that it is in meter cube per hour, okay, meter cube per second, okay, and it is not normal meter cube. So, the gas is corrected, flow rate is corrected to actual operating temperature of the ladle and mean hydrostatic pressure of the system, rho g L divided by 2. Okay. So, that is the reference state for this particular, this is L is the depth of liquid, which essentially tells me that this is what is L, and R essentially represents the mean radius of the ladle. And as I have said, there is not significant difference between this and this radius, okay, because the taper is only about 2 to 5 degrees, and that is why you can. So, if you want to write, you can write Rm, whereas the Rm represents the mean radius. What it means that the velocity is going to be fatter the ladle, there is a negative sign here, less intense for the same flow rate, less intense is going to be the flow. So, the vessel geometry has an important role to play, and here also you can see that this is about the same relationship comes, and L to the power 1 by 4 and R to the power so rough 2 by 3. This is basically close to 0.6. I have just tried to write it as 2.3. That's fine, because there is not significant changes. Again, this is also in, and this essentially represents an average speed of liquid recirculation, and the top one, the number 1 equation represents that. These refractories causes the surface temperature is 300, and the flux, if you measure, the flux is somewhere about 5 to 10 kilowatt per meter square. That is the refractory, that is the rate at which the ladle is losing, or the melt is losing heat to the surrounding. If you do not have slag, if you do not have cover, in that case the melt is exposed to the environment, then the rate of heat loss could be as high as 100 kilowatt per meter square. In an uncovered ladle, physically uncovered ladle, with negligible amount of slack covering, a significant amount of heat loss can take place, and as a result of which, during the 70 and 80 minutes of processing, we can expect that if you have a bigger ladle, temperature drop is going to be 0.3 to 0.4 degrees centigrade per minute, and the same for a smaller ladle is going to be somewhere around 0.6, 0.65 degrees centigrade per minute. So, continuous heat loss is taking place. So, you can imagine if you are processing 70 minutes, you have a 21 degrees centigrade heat loss, and similarly here you are going to have about 42 degrees centigrade heat loss. So, unless and until, and you have already lost 70 degrees in the ladle during the tapping process itself. So, you do require something, some heating arrangement, and it is that to which we will now concentrate on for the next half an hour or so, that how you really start heating. Then the heating arrangement is basically the same as electric arc heating, because there is no scope for doing any chemical heating. If you add aluminum and blow oxygen, you will make steel further dirty. So, heating of a cold melt by using aluminum and oxygen is not to be done if your ultimate objective is to get quality steel. So, basically ladle furnaces are now going to be, ladle refining furnaces are now subjected to subsequent to tapping operations and deoxidizer additions, etc. They will be carried to the LRF station where arc heating will be done, the cover will be removed, and then will be same sort of a structure as electric arc furnace, that we have 3 electrodes, a cover, and the cover will swing back on the top of the ladle, and then arcing will start, and that arcing will give us heating to the rate of 3.5 to about 4.5 degrees centigrade per minute. That is the rate of heating. And during that time, if we do not have stirring in the system, what is going to happen? Heat will be restricted. This part of the melt is going to be more heated because of the arcing, while this will remain cold, and as a result of the stirring, what is going to happen? There is going to be some thermal homogenization in the system. So, the heat from this region will be dissipated or distributed throughout, and thereby there will be more efficient heat transfer from arc to the melt. We will continue the discussion.